let's look at this triangle. We have A, B, C, X, Y, Z. Yeah. Okay. These triangles. So, like, how many triangles are here?
What?
That's the question.
1, 2, 3, 4.
Simpsons line.
Not yet. Not yet. Not yet.
Think we get off
No. We're still doing.
There's only
We're
4
still doing
triangles.
There's 5 triangles.
Where's the 5th one?
What's the rule for the
Join C's.
what's the rule for
Because A, B, X in this triangle.
We're not doing that yet, but
We're not doing minutes.
Oh yeah.
What? What? How's
Oh
the
yeah.
A?
The ratios. Yeah.
How's the ABX a triangle?
Okay,
If you
so
count that as a triangle, there's like more than
I guess there's
yeah, it's like
there's like 8 now.
I guess there's 4 triangles that are like actually connected on, right? Oh no, we're just doing this exception. Like remember how we were saying with the triangle, the orthocenter was passed through by like basically any circle that had diameter like a Sevian, right?
What's a Sevian?
It's basically the line from one point to the opposite side of the triangle.
Oh, okay. So basically a more generalized form of the midline.
Yeah, where do you think the seven theorem came from? It's like
remember seven?
the same Italian,
Okay,
same
so-
Italian guy who also
Let's see.
named these weird things.
Is it
And
clear
some
that
kind of
is it clear that the 4 triangles have
Yeah,
different
it's like a booger.
orthocenters?
Not like that. It's a booger.
All
the hell
different
that?
opposites.
I don't know how.
Sure. Yeah.
You pick your boogers.
Sure.
So like,
Me too.
Yeah. That's true.
is that kind of obvious?
What's kind of?
They have different orthocenters.
They have different orthocenters.
Yeah.
Or different triangles have different orthocenters. Or is that not?
Oh, I remember Sevian's theorem. It's like those two
Alright.
plus over that is equal to 1.
Yeah, but like we don't need it now.
Just the fact that I remember it. What is your definition?
Alright, so I guess we can just kind of just let's try and draw some.
We didn't have possible.
What do you guys do at school?
Is this cute or obtuse?
Pretty much like
Maybe the orthocenter is like here.
Like they don't really care, so they're gonna do whatever you want.
Well, the problem with
Did I draw this angle acute or obtuse?
that angle is like
Cute.
almost like a right angle.
It's a little bit obtuse. Maybe it's here then. Okay, so the orthocenter here is like there.
Yeah.
The orthocenter is like
You can go you Oh, you mean that?
Would it be like
Are they like
yeah.
here, yeah.
Yeah.
oh
They're linear.
Where's the other orthocenter? What triangles have I done even?
You have to do X, C, B.
ABC, BC1.
you I think you missed
AC1.
this one.
Oh yeah.
This one.
A
Like the one that gives you this
yeah.
this and
X, C, B.
Hang on, what?
Yeah.
You mean X, C, B, right?
Wait, what?
Yeah, that's over
Z
here.
ZXB.
It's probably like here.
Wait, isn't that top one ZXB?
No, the top
But
one is
it's A.
AZY.
X is all the way on the right.
Oh, oops.
That one's AZY. That's not AZY.
that's-
No,
Apparently,
the top one
apparently.
is DCX.
Oh wait,
Yeah.
no, the
So
top
then you
one
will
is
see AZY.
BZ.
BCX.
BZX.
Is it? No, it isn't.
Is that?
Oh yeah, that is.
Oh, that's
BCX,
So it was just bad. What did I miss?
Nothing.
You missed absolutely nothing. So the point is discussion.
Um,
And you're telling me that you want
Yeah.
to
like here.
Yeah.
Yes.
Say here.
Yeah.
Sure.
There's like one that's there.
It's like Z.
Yeah.
Wait, which one's that one?
That doesn't look
No,
right.
no, no, no. It's,
AZY.
it's inside BZX.
I can't even tell if this angle is acute or
Yeah,
obtuse.
yeah. So we've defined right now. We're using it as a
Oh,
Acute.
my diagram is.
It's like here, I think.
Oh, it's acute because wait.
Yeah.
So that's obtuse.
That one in there, so it's like here.
Okay.
Okay, this one's ooh,
Wait.
oh god, that looks weird. Because if we have this one across, so then this it's around here. I think we just call it here because why not? Oh, but then wait, isn't this one like? Why is this one here then?
My show's not very clear.
Oh, so this is the same meal. Sorry.
Yeah. Wait.
Oh, I screwed it up.
Sure.
Right, let me draw it like something more. That's one altitude. And
B to A C C.
here, yeah.
Yeah.
You're telling me they line.
Hmm?
Seems legit.
Yeah, I'm trying to tell you that they kind of lie on a line.
Seems legit.
Yeah, but the point is, like, there's some sort of symmetry between these triangles. And, so, I mean, the conclusion is they all have to, the radical axis thing has to all, like, pass through the orthocenters, right? So, because of the symmetry, they all have to pass through all the orthocenters. So, it ends up being a straight line, even though you have more than two circles.
So there's four. So the four orthocenters has to lie in the straight line. Is that
Is
like?
that like a name of this film?
So when do the four orthocenters
Not quite.
line up?
Do you have to prove it?
Are the orthocenters collinear?
What did I miss?
Nothing.
I'm gonna keep asking that until we actually get someone. Even if we get someone, we'll still say you or something.
Correct, Leo.
Because when you hear the question, is we just
Sorry,
say, did we miss anything? No. Therefore,
No,
you didn't
yeah.
miss anything. That's how.
Right.
That's how
Assuming the
advanced social.
That's not
Assuming the contrapositive.
Contrapositive. Why would you do that?
No, I mean like
Jeez.
just because we didn't miss anything.
Contrapositive. I think that's the wrong method of proof.
No, I mean like I'm supposed to prove that it's a wrong method of proof.
But it's
Yeah.
the correct method of
Proving a proof. That's kind of weird, but
That's
just like P equals NP.
Okay, so if you take a diameter with AX as a diameter, right? Yeah, I guess what I'm trying to say is, remember that argument we had where we had like the orthocenter had the same power with respect to the circles with diameters the size of the triangles, yeah?
Yes.
I'm trying to say that all of these orthocenters have that property with all these circles that have these sides as diameters.
Oh, we're trying to prove.
So all the circles have actually a common radical axis, and it's the line that goes through all the.
Did I actually? That was
Yeah, so it's possible to have like a situation where you don't just have one radical center for three circles on triangles.
What? Isn't there always a radical center for any three circles?
If it's not parallel. Here it's parallel.
You mean the circles are parallel?
The circles have the same radical axis.
Oh, okay, sure. Like this, like the case you mentioned here, right? Can the circles be have parallel radical axes that are not the same?
Okay, so maybe to see this easily, let's see what I wrote. I wrote if you have the circle with AX and you had the circle BY.
Circle BY. Circle.
I said the circle with diameter AX and BY pass through these radical centers, the orthocenters. Okay, why is that?
So what does this? Oh, so you're trying to the orthocenters of the ABC.
This is
Orthocenters. So you're trying to prove that the orthocenters of the four triangles.
yeah. So the
2016 points.
B that's BY. The BY
So. Oh, okay.
What's the theorem?
Wait, can I see that as well?
$156, yes. So 156. Just this. That's the answer, yeah. It should be 155. But yeah, it's definitely 156. So remember my answer. Oh, sorry, 6. Yeah, 156 as well.
AX, BY, and CZ. Okay, so the theorem only concerns AX, BY, and CZ.
Oh, okay.
Okay, so these three circles have one radical axis. And it's this line going through all the different orthocenters. Yeah?
Wait, how do you know this is the orthocenters are collinear?
Oh, this is proving it.
So,
So maybe I can state the theorem again. So
you're trying to prove the theorem?
four lines meet at 6 points. I'm gonna call them A, B, C, X, Y, Z, right? So that X, B, C, Y, C, A, Z, A, B, and X, Y, Z are collinear. Then the circles so then the circles AX, BY, and CZ have a common radical axis which goes through all four orthocenters.
Wait, do you mean XBC? Like the ortho.
CZ.
Oh.
you mean 1 point?
Hmm?
You mean the 1 point goes to all three?
Which?
Wait, so why did you circle that 1 point?
Oh no, I was just trying to. I had some plans about this. I was trying to say that AX, for some reason, I was saying AX and BY clearly pass through these three things. But it's not as clear now.
Maybe
The
Yeah.
HABC. So HABC means the circle. Doesn't mean the orthocenter of this.
Yeah, so if you look at AX, right? AX will pass through that.
Isn't that red dot by definition the orthocenter of ABC?
Yeah.
wait. Which try?
And H.
Isn't that like ABX?
A,
And now you've got the same structure with.
B, X.
Wait, don't you now have the same structure? 1, 2, 3, 4, 5, 6 points.
Because you drew in the bounding model of X.
Oh, I guess that would be
So it shouldn't be from C if you want to do it that way.
yeah, you're right. But did I just never join in the ABC orthocenter?
Like I think that was the one you just drew in, and then you just like accidentally drew from X.
So this is not. This is.
ABC.
So that's this one, right?
Yeah.
Yeah, that's good.
That's in C.
And
Huh? If we have BY as a diameter, then the altitude. What?
the altitudes are outside of the triangle.
ABC. Yeah. It's there, right?
Mhm.
And where's the altitude?
There.
Yeah.
And the other altitude.
So then that shows that the circles AX and BY have radical axis passing through HABC, the black holes.
Wait. Oh, okay. Right. Okay, A, B, C, and A, Z, Y.
Yeah, so the solid two, so these 2 points here, right,
Yeah.
lie on the circle of diameter AX.
Yes.
Oh no.
What?
Hold on.
They lie on AC.
Yeah.
Yeah, they do.
No, the line. Yeah, AC.
Yeah.
One of them lies in AX, another lies in
Yeah.
CC.
Yeah, so I guess the point is AC and AX are coaxial, so they have the same, like,
Oh, yeah.
Huh? Oh, okay.
so
Yeah.
if this has the same power for AC, then it has the same power for AX.
Okay.
Wait, correct? They have the same. Have the same resultant axis.
Wait, is that true?
Yeah, cause like they're 90 degrees. That's 9 degrees. That's 9 degrees.
Yeah, so basically,
So that passes.
the diameter AC and AX, right?
Yeah.
They both intersect at
Ah.
here and A,
Oh, right.
so their radical axis goes through there.
Yeah.
So that point has the same power for those two.
Cool.
Yeah. So then, so that times that. Yeah. So that page times that part is the same as this times that part. Yeah.
Doesn't look like it.
Well, wait. How'd you get the like half of C?
Yeah, so on the circle with AC, right? This is just 1 point with that power and this power, right? And they're the same.
Oh.
Okay, but it has the same. It's on the radical axis as with AX, right? So then it has the same. Yeah. So what are we trying to say to make this conclusion? BY. Yeah. So we need like this times this, right? To equal. So the same thing on the other circle. This times this. Yeah. So this times that is the power of this point with respect to the BY circle, yeah?
Yeah.
Oh.
And then this times that is the power with respect to
the C whatever circle.
I mean, you know that.
Yeah.
You know
to the AC circle, but it's the same as for the AX circle.
Huh? The C.
Yeah. So the point is it lies on the diameter AX and BY radical axis. Yeah.
Yeah. Okay.
So I guess if you were convinced that like the arguments before showed that a lot of these orthocenters had to lie on there, you would check these facts with a lot less suffering, I guess. Does that make sense?
Yeah.
So like, yeah, one is like checking each one, not knowing if it's going to be true, and the other way is like doing the same thing, but being happy that you're already it's already going to work out before you do it. So is it clear that this lies there, right? And then I guess you can do something similar for A, Y, Z. A, Y, Z. Huh? A, Y, Z. So that's this one here. Yeah, but I guess the point is it doesn't always. So you have 3 different circles, right? And they're all like different Sevians of a triangle, yeah? And there's no such thing as a radical center, yeah? So just because they pass through the orthocenter, like they all pass through the orthocenter, doesn't mean that orthocenter is the only point on that line, yeah? So in this case, there's 4 different orthocenters that all lie on the line, yeah?
So why is there no radical
So
center?
the other theorem was that like they pass through the orthocenter, right? When it's like, and that is the radical center when they're not all coaxial, like they don't have all at the same radical axis. And this gives you the situation basically. So the special situation happens when you have these 3 things being collinear, I guess.
Huh?
Yeah.
Which 3?
X, Y, and Z.
Oh,
So it's
okay.
X, Y, and Z in this case. Yeah. But then obviously if you have X, Y, and Z collinear, right? You have like the symmetry.
BC and X,
BC,
collinear,
X
BZ and A
collinear.
collinear.
AZ.
Also, that's why when you draw circles,
Yeah. Like you can
X,
view
Y,
it. You can
Z.
view it as like a triangle with one point here
Yeah.
that makes this collinear, right? Or you can view it as like this other triangle with this point. Then, yeah. But the point is, it's not just one point. There's 3 circles. There's one radical line, yeah, instead of a radical center. Okay.
Oh, okay. So that's the equivalent of like 3 points with a triangle that don't form a triangle because it's collinear. Okay.
Yeah. I think that was it for this part. It's almost dinner time. Yeah.
Wait. So what's this?
I already so good. No, never mind. It's so much.
What are you trying to say? My mom.